This is lecture number 23 in the FOA series on fiber optics. In this lecture, we'll look at total internal reflection, the optical phenomena that makes optical fiber possible. You're probably quite familiar with this drawing, which shows the core and the cladding of the optical fiber covered by a protective buffer coating. The core is where the light is transmitted, and the cladding traps the light, contains it within the core by a phenomena that we know in optics as total internal reflection. When light travels through the interface between two materials of different optical properties, like water and air, as we see with this stick stuck into water, the light is refracted, or the angle of the light changes. And that's what makes a straight stick we push into the water look as though it's bent. The index of refraction is the speed of light in a material. And if we choose the core and cladding in optical fiber of the proper types of material, the light will be bent toward the core of the fiber at all angles. At a certain angle, the light will be bent enough to actually be trapped inside the core of the fiber. And this is what we call total internal reflection. You can see this on the diagram of a step index optical fiber that we show below. As the angle of the light becomes shallower and shallower, at some point all the light is trapped in the core. Well, we can take a step index fiber like that and a beam of laser light that's visible to us, and we can actually demonstrate this phenomena. We're going to do it with a large core step index fiber. The step index fiber we're going to use is a very large core, about 12 millimeters, and is typical with plastic optical fiber. It has a large core and a relatively thin cladding. That makes it very, very easy to demonstrate total internal reflection on this particular fiber. Let's look at what happens. Here's another interesting experiment to do with a visual fault locator. What I have is a large plastic optical fiber. It's about 12 millimeters in diameter and has a very high numerical aperture. But it shows us very effectively how total internal reflection works in an optical fiber. So I'm going to take this connector from the VFL and couple it into the plastic fiber. And there you can see that we're getting a lot of light out of the far end of the fiber. I can move the connector around and get slight changes in the far end of the fiber, but nothing significant. But look what happens when I start going off at an angle. Now we're starting to get strange patterns on the far end of the fiber, and now at an angle, a very high angle, because it's a very high numerical aperture fiber, we're now losing all the light into the cladding instead of being kept into the core. This is how total internal reflection works. The difference in the index of refraction of the two materials in the core and the cladding cause the light to be trapped inside the core. So now I'm just going to reduce my angle a little bit. It didn't take much, and now we have total internal reflection again. And that's how it works. A simple demonstration with a visual fault locator and a large core plastic fiber. More technical information on fiber optics is on the FOA website and our FOA online reference guide to fiber optics and tech topics. We're the Fiber Optic Association, the professional society of fiber optics.